Subtopic B of the 2018 call addresses the mid-term future in the orbital robotics realm. OG8 will implement the AIM, which is related to robotized assembly of large, modular orbital structures. A constant trend in space development is to create larger and larger systems in orbit. This development is limited by the volume available in the fairings of space launchers. Robots may help in deploying space structures from the confined volume of the launch configuration to the expanded form needed in operation. The objective of OG8 is to explore and understand the robotic capabilities required to autonomously assemble large structures in orbit. Specifically, OG8 will focus on the concrete case of assembly of orbital telescope mirrors, composed of hexagonal segmented tiles. Larger telescopes will enable scientists to see farther into space, and in far greater detail, hugely improving our understanding of near and deep space. But presently we are limited by the limits of space within the spacecraft thus for self-deploying structures. Successful robotic assembly could overcome this problem. OG8 will rely upon two robotic systems. OG8 focuses on telescope mirrors larger than that mounted onto the James Webb Telescope, currently considered by many to be the largest mirror array that can be contained and self-deployed from within an existing spacecraft. Thus, OG8 will explore advanced autonomy, manipulation, mobility and the ability to work to predefined schematics to achieve a complex, desired design. A robot that is able to assemble 6 tessellated, hexagonal tiles 1.3 meters in diameter, and a mobility system, mounted and integrated into the spacecraft platform, which will enable the robot to travel across the tiles to create ever larger rings of the telescope. This system will enable the evolution of future telescopes as shown here, with the ability of assembling mirrors of increasing size. As with all the OGs in this call, OG8 is required to integrate and adapt the Call 1 building block products into a system that will satisfy the criteria of the robotic assembly system. This will mean tailoring the autonomy system to plan and execute tasks based upon an existing schematic of a telescope mirror, determining the configuration of the sensor suite and 8 fusion systems, and finally producing the requisite number of serum interconnectors needed to join all the mirror tiles together. The demonstration will comprise the following elements: a demo spacecraft platform, which will act as the storage bus and base for the mirror, a demo robotic assembly system, which is able to manipulate the individual tiles to remove them from the bus, attach them to the spacecraft base and or other mirror tiles, and demo segmented mirror tiles, which are to be assembled to achieve the predefined design. The demonstrator will comprise of 2 stages, the assembly of the inner ring of tiles, and the assembly of the outer ring of tiles. The assembly of the inner ring starts with the deployment of the robot itself. The robot must be deployed in such a way that it can then retrieve the first 4 tiles, tiles 0-3. The robot must be able to grasp, remove, manipulate, connect and release the tiles. The first 4 tiles will be assembled as so. Each connection point will be enabled using the serum interconnector. The inner ring is complete. The assembly of the outer ring must be achieved by the robot traveling to the outer reaches of the mirror. The robot will retrieve the last 2 tiles and carry them to the desired location using a mounted mobility system, such as a monorail, a walking arm, or other system of the consortium's design. Once at the outer edge, the robot will fix the final 2 tiles in place, achieving the desired design. This entire demonstration scenario shall take place in an orbital simulation facility.